afternoon of Thursday for our talks. I'll be sharing a couple talks here. And our first speaker that I'm pleased to introduce is Bjarki Holm, who's going to be speaking about how you can add linear algebra operators specifically over finite fields in an attempt to capture logics for p time.
Right, thank you. Yeah, so as Stephen said, in this talk I'm going to discuss some recent work that has been done to study the definability of natural problems in linear algebra and the expressiveness of logics with various kinds of algebraic operators. So just to give you a bit of an overview, so after giving you some of the context and motivation for this work, I'll go on to look at some of the descriptive complexity of elementary matrix properties, which leads me to study logics with operators for matrix rank over finite fields. And in the final part of the talk, I'll discuss some recent work on defining pebble games for such logics and how they relate to the well-known Weisweiler-Leman method for graph isomorphism. So I'll begin at the beginning of descriptive complexity, which was essentially initiated by the theorem of Ron-Fagin in 1974, which says that a decision problem is in NP if and only if it can be defined in the existential fragment of second-order logic. And the intuition behind this proof is quite nice. So essentially, if you look at the format of the structure of formulas of this logic, then essentially it can be seen that the existential guessing of the second-order variables corresponds to the guessing phase of a non-deterministic machine, and the first of the formula that follows can be seen as the verifier of those relations. So this result naturally raises the question whether there's a corresponding logic for p time, and this essentially is the context in which this work that I'm going to describe is set. So the logic that has been studied, or the logics that have been studied most extensively as candidates for this for such a relation have been the extensions of first-order logic with inflationary or least fixed points. So in this talk I'm going to focus on inflationary fixed point logics. And this, by the way, if you attended Albert's talk on Tuesday, then he mentioned some of these results. So I'm going to just recap them quickly in the next few minutes. But so the first major result, or the first result for a capturing on a nice class of structures, was given by Immermann and Vardy in 1982. And this theorem says that a property of ordered structures can be decided in polynomial time if and only if it can be defined by a sentence of fixed point logic. So here by an ordered structure, we mean structures whose signature has a special binary relation symbol, which we interpret as a total ordering on the vertices. So despite this capturing on ordered structures, if we drop the requirement of an ordering, then there are some very simple properties that we cannot define with fixed point logic. And this has been mentioned in some of the talks before. So in particular, the logic is not strong enough to tell you whether a graph has an odd and even number of elements. So the natural thing that was done in the late 80s, I guess, 90s, was to extend fixed point logic with some kind of mechanism to allow to count the number of solutions to formulas. And this gives us fixed point logic with counting, FPC. And yeah, I guess from late 80s and well into the sort of and still today, this logic has been studied extensively, and there is still very active research going into looking at which kinds of natural classes of graphs, let's say, suffice to give us a capturing for this logic. And I'll just quickly mention some of these here. So first of all, since fixed point with counting is an extension of fixed point logic, we have this obvious capturing on ordered structures. And if you drop the ordering requirement, then we have various results relating nicely behaved classes of graphs to definability in fixed point with counting. So on the class of all trees, this logic captures p time. This was generalized to planar graphs a few years later. And another extension of the tree result was given by Grohe and Marinho in 1999, which says that on any class of graphs of bounded tree width, we have a capturing result. And most recently, all these results were generalized by Grohe with a big, 300-page paper, I think, or book that sort of shows that for any minor closed classes of graphs, fixed-point logic with counting captures p-time. And apart from these nicely behaved graph classes, it can also be shown that essentially on the random graph, there's a formula of fixed-point logic with counting that suffices to define a linear ordering almost surely. So so this logic captures p-time on almost all graphs in that sense. So the question is naturally whether we can close this gap. And as you probably know, the answer is negative. But before I give some of the counterexamples to that sort of conjecture, I'll start by mentioning how we can actually prove non-definability in this logic. And again, this was described in some detail by Albert on Tuesday. I'll just recap quickly. So the idea is that we, rather than focusing on fixed-point logic itself, we sort of translate to domain of finite variable logics. So I'll write for a natural number k, I look at the sort of k variable fragment of first logic extended with counting quantifiers of this kind. So the idea is that for every natural number I, we have a quantifier of this type, and the semantics is that this formula holds in a graph if there are at least I vertices that satisfy the formula phi. Okay, so I'll mention a couple of facts about the relationship between counting logics and sort of finite variable counting logics and fixed-point logic with counting. So first of all is that every formula of FPC is invariant under CK equivalence for some value of k. And secondly, that we can characterize CK equivalence by a pebble game, which is an extension of the Ehrenfeucht-Frasse game. So what I mean by characterized in this sense is that two graphs G and H agree on all sentences of CK, if and only if duplicator has a winning strategy in this k-pebble game on G and H. Okay, so with these two facts, we essentially have a general method for proving non-definability in fixed-point with counting. So the idea is that to show that a property P is not definable in this logic, it suffices to show that for each k, we can exhibit a pair of graphs, gk and hk, for which one of the graphs has the desired property P, the other one does not, and the duplicator has a strategy to play the pebble game, forever on G and H. So this shows that there's no fixed k that sort of for which the property P is closed under CK equivalence. And another property of these games that I'm going to mention here and come back to later in the talk is that it's known that these k-pebble bijection games are sort of intimately related to, well, first of all, sorry, I'm going to mention that for each fixed value of k, we can decide the winner of the game, so whether it's spoiler or duplicator, we can decide the winner of the game in polynomial time, in the size of the two graphs. And secondly, I mentioned this close connection between the CK equivalence and the pebble game and a family of algorithms for graph isomorphism, which probably many of you know and is known as the Weisfeld-Lehmann method. So towards the end of the talk, I'll show you how we can sort of derive a corresponding algebraic version of this method from some of these new games that I'll talk about. Okay, so this brings me to an application of the game method, and this was shown by Zeifer and Immermann in 1992. And they show that there's a polynomial time decidable property of finite graphs, which is not definable by any fixed sentence of fixed point with counting. And so I'm not going to talk about the actual construction that they give, which is quite ingenious but complex. But it can be seen from their construction, if you analyze the kinds of graphs that they use, is that this shows that fixed point with counting does not capture polynomial time on graphs of bounded degree. So even degree 3 suffices here. Nor does it capture polynomial time on graphs of color graphs whose color classes are bounded by whose size of the color class are bounded by a fixed constant. And here it suffices to look at color classes of size 4. The problem, well, the issue one might have with this is that this is not the very natural polynomial time property separating fixed point with counting from p-time. So in recent years, a number of people have started to look at sort of problems in linear algebra and see how sort of which of these,
What is a natural graph property?
something that you might sort of encounter in practice, I guess.
Practice.
Well, define practice. Well, I mean, so these are very, clearly very artificial counterexamples rather than being, well, like some of the problems that I'll mention later on. This is not my view, let's say. So someone might say this. So.
You used to say, for instance, Eric Davis said this in the mid-90s, that fixed point counting can express every natural property.
Natural is whatever is definable by FPC,
Well,
right?
Yeah. But in the sense that you have to go to artificial constructions to find it. It turns out, in some sense, he's wrong. I mean, we convinced him by actually coming up with things which he agrees are natural.
But even, this was long time ago. The thing had to do with counting. There were previously things of that nature, even before that.
So this is a quote by Eric
This
Craven.
world, kind of property with counting, that the logic that, they require essentially algebra.
All right. Okay, so this brings me to problems in linear algebra, which are more natural. So in order to explain what I mean by looking at definability of matrix properties in as finite structures, we'll have to formalize exactly what we mean by matrix in that setting. So, I mean, in a usual textbook on linear algebra, the usual notion of a matrix is as an array of elements. So indexed by, you have m rows and n columns, and you essentially have a natural ordering on the matrix in that sense. So if that's the way in which we look at matrices and sort of matrix properties, then clearly there's nothing to be done because we have an ordering on the rows and columns, and we can define every property in polynomial time. But the point is that, I mean, there are many natural, I'm overusing this word, sorry. There are many nice matrix properties that are nice, okay. that are clearly invariant under, right, okay, nice. It's very vague.
Already taken the word natural.
No. My point was it belongs to everybody.
Okay, nice properties that are invariant under permutation of the rows and columns of the matrix, so rank, determinant, etc. So I mean, so more specifically, these are properties of the. So these are really properties of the underlying linear map rather than the matrix representation. So we're looking at properties that are invariant under the choice of a particular basis, and so on. So in that sense, it makes sense to look at a matrix that's not given by an explicit ordering on the rows and columns. So what I mean by that is we have a pair of finite and non-empty sets I and j, and D is some kind of domain. And by an I by j matrix over D, I really just mean a function from ij to D. So given a sort of row I, column j, this function gives you the element of the matrix in that position. And similarly, we can formalize a system of unordered systems of linear equations in this sense. So now you have a I by j coefficient matrix, j indexed vector of variables, and an I indexed sort of target vector. And if you want to formalize this as some kind of relational structure, I'll mention one way in which you can do it here. So if you have a fixed domain D, which is what the theorem I'm going to talk about next considers, then one way in which we can represent this kind of system as a finite structure is by considering a signature where there's a binary relation for every element of the domain, unary relation BD for every domain element. And the idea is that for every D, so for example, if you look at A0, let's say, then this tells you which positions of the matrix have a 0. A1 tells you where the 1s are, and so on. So you can assume they're disjoint. Otherwise, you can take a sum over these things and so on. I mean, clearly, one can also formalize systems of equations where the domain is given as part of the input bytes. Like if you have a finite ring, let's say you're given the tables of the ring. But this fixed domain actually suffices for the next result, which is given by Tseres, Bulatov, and Davar in 2007. And they showed that the problem of defining or deciding solvability of systems of equations over any fixed finite abelian group with at least two elements is not definable in fixed point with counting. So this is a very nice property, I would say, which is not in fixed point with counting. And so if you consider a fixed finite field, then obviously this implies that the same result holds for definability over finite fields. And from elementary linear algebra, we know that to determine solvability of equations over a field, it suffices to compare the rank of the coefficient matrix of coefficient matrix A and the rank of the matrix A with B adjoined as a column. So it suffices to check whether these two have the same rank. And this shows that the essentially matrix rank over a finite field is not expressible or definable in fixed point with counting. Okay.
You mentioned the determinant.
Yeah. So
How is that?
yeah. So this leads to the question: sort of which other properties are definable, if any? And we can actually show that in fixed point with counting already. If you consider matrices over the integers, the rationals, or any finite field, we can define this should be any finite ring even, which is extended by Pacusa. But we showed in this paper in 2009 that these properties can be defined in fixed point logic with counting. The same holds for the inverse of an invertible matrix. And over the rationals, we can actually define the rank of a matrix in fixed point with counting. And all these results are valid even when you have the domain given as part of the input, not just fixed. And we can also define the minimum polynomial of a square matrix over so we showed this over the rationals, and then Pacusa extended it to the finite fields. And I mean, these are very sort of common elementary properties that all of them seem to be definable in fixed point with counting, and the one that's not is rank over a finite field.
Sorry, you said that all these holds if your domain is given?
Yeah, so
that it's fixed.
sorry,
Number 3, for example.
number 3, yeah. So over the rationals, you might be given some bound on the size. So you're given the elements in binary, let's say. So you have a sort on the side that sort of gives you the index sort for the elements of the matrix, and that has an ordering, but not the matrix itself, let's say. And you can show that the intermediate values you need to define are bounded by polynomial in the values you're given. Okay, so in the rest of this talk, I'm really going to focus on sort of this property of defining the problem of defining the rank over a finite field. And in the talk that follows, the next speaker will talk about some of these more general problems, so solvability over arbitrary rings and arbitrary finite rings and groups. Okay, so this led us to extend fixed point logic with, just like fixed point logic had been extended with a counting operator to allow it to express counting properties. We considered an extension of some sort of matrix rank construct. And let me first just say what I mean about definable matrices in this setting. So I say recall, but I don't think I've said this. So we can take, if you take any binary, so I said before that a matrix over a G of 2, I by J matrix over G of 2, could be seen as a function from Ij into the two-element set. And clearly you can take, if you take a subset of I cross I, then you can associate that with the characteristic matrix of that set. So we view that as a matrix. And now if you have a formula phi with two free variables and a graph G, then I'll write m phi G for this for the matrix defined by phi over G. So I'll see this as a two-element matrix over the two-element field. And this is defined, so if you take any vertex u, any vertex v, then the uv entry of the matrix is given as 1 if the assignment of u to x and v to y satisfies phi in G, and 0 otherwise. So for example, if you take phi to be the formula that says that there's an edge between x and y, then this matrix is just the adjacency of the graph G. And so more generally, we can obviously formalize matrices over arbitrary prime fields by allowing sort of elements other than 0, 1, but not really important for the rest of the talk. So I'm just going to focus on 0, 1 matrices. Okay, so this brings me to fixed point logic with rank. In this setting, we have two types of variables. So either normal sort of vertex variables, range over the element of the graph you're trying to model in, and you have number variables that range over the natural numbers. So quantification over the number sort is bounded by some term. So a number term in the logic, and to build number terms, you have essentially, to relate the vertex sort and the number sort, you have these rank terms of the following kind. So for formula phi, you have a term of this kind. And the semantics is that this is the element of the number sort that represents the rank of the matrix over G of P. So over the number sort, you have the standard arithmetic addition, multiplication, ordering of the numbers. So this is similar to in Albert's talk. Well, not similar. So in his talk, you looked at sort of finite sort of numbers from 0 to n, and it can be seen that sort of these two formalisms are equivalent in the sense you can translate between them. And this gives us fixed point logic with rank over a fixed prime over arbitrary primes. We allow different primes to occur in formulas, and similarly extensions of first order logic with rank over a prime field P or arbitrary prime fields. And the first thing to observe is quite trivial, that for any prime P we can express solvability of equations over the P element field. And we can actually stand this for arbitrary fields of characteristic P. The idea is that if you're given a system of equations over the field of cardinality P to the m, then we can find the representation of the elements of the field by certain kinds of matrices over G of P. And this allows us to build up a bigger system over G of P, which is equivalent to the first one. And by observing that we can actually express counting by using rank terms of diagonal matrices, we get this inclusion of fixed point logic and counting in fixed point logic with rank for any prime P. And this result above tells us that we can actually get a proper separation of the two. So if you look again at these CFI graphs, they were the original counterexample to the conjecture that fixed point counting would capture P. Then we can show that even in first order logic with rank over G of 2, we could distinguish between these classes, or define this graph query that they considered.
Can you go back one slide?
Yeah. Sorry.
How did you get the inequality then?
So we cannot define solvability of equations. We cannot define solvability of equations in fixed point
This
counting.
FPCO comes squared.
Sorry. Yeah. Yeah. So the idea of this theorem, I mean, so essentially this is shown by giving a simple first order reduction from the CFI query to solvability over G of 2. And if you remember that the CFI construction showed that we cannot capture P time on graphs of color class size 4. And we can show that isomorphism on such graph classes can be expressed also in first order logic with rank over G of 2. And so there's some hope that this can be extended to logic classes, but that's in progress. Okay. Right. So this brings me to the next topic. So I mentioned before that to prove inexpressibility in fixed point counting, we generally use these game methods. So we translate from fixed point logic to finite variable logics and show the existence of graphs which you can play for every k. And we would like to get something similar for these rank logics. So first of all, we want sort of a pebble game for finite variable rank logics, which characterizes equivalence in k variable rank logic. And it would be nice, so that would be nice. It would be very nice to get these following two properties. First of all, that we can actually decide the winner of the game in polynomial time. And also it would be nice to have some sort of correspondence between that game and a kind of stable coloring method like we have for the counting game. And we can show, and I'll sketch this in the next few slides, that in the first case we have a game which I'll call the matrix rank game. So this game exactly characterizes equivalence in finite variable rank logic. The problem is that it's hard to play, which is kind of expected, but it doesn't really behave so nicely when it comes to these two other properties here. So what we also do is we consider an extension of the game, or rather a restriction of the game rules, so sort of makes it harder for duplicator to win the game. And it turns out that this game actually gives us these two very nice properties that we were looking for. Okay, so in order to express these games, we'll first have to, just like we did with the counting logics, go into the domain of finite variable logics with rank quantifiers. So again, we look at first order logic with only k distinct variables in each formula. And now we have these rank quantifiers of this kind. So this is distinct from the these rank operators that I had before. So we only have a single sort in this setting. And we essentially have a countably infinite supply of these quantifiers, so one for every I. And the semantics is, as before, this tells you whether the rank of the matrix defined by phi is at least I. And so it's not hard to show that every formula of fixed mode logic with rank over G of P is actually invariant under this RK equivalence for some K. Secondly, that this equivalence can be characterized by this K-pebble rank game that I'm going to describe next. And this again means that two graphs agree in all sentences of RK if and only if duplicate has a winning strategy in the game. So the rules of this game are fairly complex. I'm going to describe them quite sketchily, and I'll save my time for detail for some of these stable coloring procedures later on in the talk. So I'll just give you the idea of the game and show you how we can modify this game to get this stronger game result. So this is a pebble game as before. You have a pair of players, spoiler, duplicator. Spoiler trying to show that the two graphs are not equivalent, duplicator trying to hide any difference there may be between them. But the difference between this kind of game and the traditional pebble game is that we have essentially a protocol which is based on duplicator having to partition the game board at every round into disjoint 0-1 matrices. So over G, she defines partition of the graph G into 0-1 matrices, same for Hades, and she gives some kind of correspondence between the two. And then there's this algebraic game rule, which says that having given this kind of partition, duplicate has to ensure that every linear combination of the matrices over G has the same rank as this corresponding linear combination over Hades. I'm not, this is very sketchy, but sort of. But the problem essentially with this is that we don't really know whether we can decide the winner of the game in polynomial time. And I mean, the natural way to test it would be to essentially carry out the game strategy. And the problem really is with this condition of checking every linear combination of these partition matrices. So if you have a graph of size n, there are n squared possible matrices you can have, and you have an exponential number of checks to make. Okay. So what we do instead is to actually look at a way to strengthen the rules, in the sense that duplicator has to, it makes it harder for duplicator to win the game. So this is done by this idea of looking at the simultaneous similarity of collections of matrices. So we define this as follows. So if you have two tuples of n by n matrices over a field K, then we say that these are simultaneously similar if sort of any pair of, so AI is similar to BI, and they're all similar by the same similarity transformation S. So it's a fixed matrix S which relates all of them pairwise under similarity. And so I don't think it's known in general whether this can be tested in polynomial time, but there's a result by Chistov, Karpinski, and Ivaniov from 1997, which says that if you look at this problem over finite fields, then you have a polynomial time algorithm for testing, and the runtime of the algorithm is polynomial in the size of the field, the number of matrices, and the dimension of each matrix. So we can use this result to essentially look at a game based on playing by invertible maps rather than by ejections, as was done in the counting game. So again, this game, this invertible map game, is again played on a pair of graphs, G and Hades. Again, we have this protocol based on partitioning the game boards into partition matrices. But now we replace the rule we had before with a new game rule that says that at each round of the game, so rather than looking at all the linear combination over G and all the linear combination of matrices over Hades, duplicator has just to ensure that if you take the collection of matrices over G and you look at the corresponding collection over Hades, indexed by the same index set, and these two have to be simultaneously similar. Okay, so using the algorithm from Descriptive, we can actually show that there's a way to check the winner of the game in polynomial time. And we can show that this, the game equivalence given by this invertible map game actually refines the RK equivalence. So in the sense that if duplicator wins the invertible map game on G and H, then C will also win the matrix rank game on G and H. So which brings me to this second point on the wish list.
Question?
Yep.
Go
Back.
back.
Yep. Sorry.
So if it refines, what does it correspond to?
So that's the question. So we essentially started in the previous case. We started with a logic. We had a game. Now we modified the game, and one of the questions is whether this actually has a logical connection, which would be very interesting. And it's not very clear how to extract the kind of structural information from the simultaneous similarity. That,
Do you know that this is stronger? This strictly refines?
yeah. No, sorry. It refines. We don't know.
You don't know
strictly,
what this is.
yeah. So I mean, yeah. So it is really an open question whether you have equivalence of the two games, and that can be stated. I mean, there are some. You can state it quite formally what the condition has to be.
So the equivalence defined by the logic, you don't know whether it's in P time.
That's right. Yeah.
One natural way of showing that the games are at least closely related would be to take that simultaneous similarity polynomial time algorithm and express it in P rank.
Yeah.
We could do that.
That would be the.
We would,
Right.
That would be the one approach. Okay, so now I'm going to talk about, in the last part of the talk, I'm going to sort of talk about some connections with this invertible map game and a stable coloring algorithm which resembles or extends the Weisweiler-Lehmann algorithm for graph isomorphism. So let me just I'll start by recalling the definition of Weisweiler-Lehmann. So in the basic case, this is usually known as stable coloring or color refinement. So this is how I phrase. So Weisweiler-Lehmann refinement essentially is a procedure that takes a graph and produces an equivalence relation on the vertices of the graph. So usually this is actually presented as a labeling procedure. So you output sort of labels on the vertices of the graph rather than just an equivalence. But this formalization makes it easier to actually go into some of the other games, or the other algorithms. So the idea is that this procedure inductively defines essentially an equivalence by starting with some elementary equivalence and then refining it in some polynomial number of steps. So at the initial stage, we say that two vertices are equivalent if and only if they have the same degree. So in this example, I'll label all the vertices with their corresponding degree. And looking at the two vertices U and V here at the bottom. And during the refinement, we say that two vertices are I plus 1 equivalent if and only if they were I equivalent. So it's a refinement. And if you consider every equivalence class, every I equivalence class, then it has to be that this class has same number of neighbors to U as it has neighbors to V. So in this example, if you take alpha to be the class of all vertices of degree 2, then it can be seen that U has only one of these, whereas V has two of these. So they can be refined, so they can be distinguished with the first refinement step. So this refinement on a single graph can be turned into an isomorphism test. So this, in this case, you're given a pair of graphs, G and H, and you want to tell whether they're isomorphic or not. And the idea is essentially that we compute the refinement on the two graphs simultaneously. if you look at the equivalences sort of within and across the two graphs. And once we've computed this, we test for isomorphism by seeing whether there's an equivalence class of the final refinement, which has different number of elements in G from H. So in other words, the two graphs will be isomorphic by this procedure if every equivalence class can be split into two equal sized parts, one in G, one in H. A couple of facts about this algorithm. First of all, this is known to run in polynomial time. And secondly, it can be shown that this essentially works correctly on almost all graphs. So again, on the random graph, this the refinement given by Weiss-Lehmann will almost surely refine every vertex into a singleton class.
Under what distribution? Uniform?
Yeah. And I think, there are different sort of, there are explicit formulas telling you sort of if you have a certain number of rounds, you get this kind of probability and sort of exactly relating the number of refinements as well. But it can also be seen that if you take a very simple graph, like two non-isomorphic regular graphs of the same degree, then this, if you look at this the iteration step, so clearly in that step they would all have the same, all be put in the same equivalence class at the first step, and the refinement wouldn't really get off the ground because they're regular, so there's nothing to distinguish any two vertices. So on these kinds of regular graphs, this will simply fail. So the idea is to extend this into higher dimensions, or sort of to look at sort of colorings or equivalence classes of tuples of elements.
Can you get an isomorphism out of this in the yes case if it says if the graphs are isomorphic? Can you actually produce an isomorphism?
So the idea, so best you can hope for is to get the orbit equivalence classes of the graph. So if they're isomorphic and you can define that, then you can look at the mappings within each of the two orbits, or the corresponding orbits. And clearly, if it refines the graph down to singletons, then like usually, yeah. So the equivalence classes will be unions of orbits of each graph. And so this simple Weiss-Lehmann test is actually used, I believe, in even sort of fairly robust commercial isomorphism tests, like NAUTI or NAUTI. It's often used as a first sort of kind of refinement step, and then if you haven't produced singletons, then you apply some more complex algorithms and heuristics to actually try to find mappings between the two. Okay, so in order to define this,
You just like the symmetry by choosing 2 points.
Yeah, you can do it. Yeah,
And you give them a special color,
and you recolor.
and then you do
Exactly.
it.
Yeah.
Now you've increased the complexity. Now it become right because you're n squared, so now it's into the.
Yeah,
And then you can keep doing it.
exactly.
It's just you pay a higher price.
Right. So if you can do it by a fixed number of recolorings, then clearly you have a test. So. Okay, so in order to define this higher dimension of Weiss-Lehmann, I'll need some notation. So I'll define what I call one-element extensions in a graph G. So we consider, if you consider a class of k-tuples alpha, a particular k-tuple U, and an index of the elements of U. Now that this sort of gamma I UA, which we can call the I extension of U into alpha, sorry. So we'll define this as the set of all vertices that if you replace the ith component of U with W, you get a member of alpha. So it's ways in which you can extend the tuple U to get a tuple in alpha. So for example, if we take K to be 3, and I let alpha be the set of all triples that realize a triangle, and I look at what these colors can be seen. So I'm looking at the triple U, V, and W here. This should be a 2, sorry. So you can see that if you replace the last component, so you fix U and V, and you look at the vertices that, if you replace W, you get a triangle, then you essentially get the two vertices A and B. And if you take gamma 1, then you're looking at the vertices that you can replace V with, so you fix W and U, and you think of the ways in which you can get a triangle by fixing these two and putting a third point, which you cannot do. So that's empty. So, I mean, if some of you are familiar with Weisel-Lehmann, this seems a bit strange way to define it, but again, this becomes kind of easier to define the algorithms that I'll look at later. But with this notation in mind, we can define the k-dimensional Weisel-Lehmann refinement. So again, we're given a graph, and we want to produce an equivalence on k tuples of the graph. So we'll start by coloring, sort of associating two tuples if they have the same atomic type. So if their induced subgraphs are isomorphic. And during the refinement step, a lot of definition. So we say that u and v are n plus 1 equivalent. If, first of all, they're m equivalent, so we're refining the equivalence. And if you consider every index I, you can find the bijection, which maps the I extension of u into gamma to the I extension of v into gamma. And this has to be for every equivalence class. So for every I, you have essentially, so f, the bijection f depends on I, and this is to hold for every alpha.
The way you put it doesn't look polynomial at all.
Yes, yeah, but the whole point is you can implement this as a,
Is gamma I here?
yeah, so gamma I is, that was this extension of all the points which you can replace the ith component of u with to get something in alpha. Okay?
Well, bijections there are many. V factorial bijection.
Exactly. I mean, so the point is that this formalization doesn't make it obvious how you would. Yeah. Yeah.
How do you need to truly check for the cardinalities of the equivalence class?
Exactly. That's how you would implement. Yes. So the reason I phrase it like this rather than in the usual sense is because I'm going to replace this bijection with something else. Okay. So so here we can show that two tuples are equivalent in this sense if and only if they agree on all k variable counting formulas in the graph G. And again, we can turn this into a procedure for isomorphism just by producing the equivalence and comparing across the two graphs. And for a fixed k, it can be shown that this is, this actually runs in polynomial time. You wouldn't have to do it naively, but you actually have to look at cardinalities of these equivalence classes. However, it follows from the counterexample given by Seifer and Immermann that we can actually find a sequence of graph pairs, non-isomorphic graphs, for which, so this should be a theta here. So they have a linear number of vertices in n, but they're not distinguished by the n-dimensional Weisel-Lehmann. So previous to this result, it had essentially been conjectured that maybe there's a fixed dimension of Weisel-Lehmann that would suffice to actually define correctly graph isomorphism. And this shows that very strongly that that's not the case. Okay, so in order to define an extension of this algorithm, I need to look at not one-element extensions, but two-element extensions, very much like before. So you have a class of k-tuples, a tuple u, and a pair of indices with, I'm going to assume are distinct here. And so the ij extension of u into alpha is just a set of all pairs, which if you replace the ui with a and uj with b, you get an element in alpha. So since this is a binary relation on V, we can see it as a matrix. And for example, I'll take the same setting as before. We have k equals 3, and alpha is the realization of all triangles. I have a different graph now, so we have u, v, and w that I'm going to fix. So if I look at the 1-2 extension into alpha, so that means I'm going to fix u, let the other two vary, then it can be seen, for instance, that I get a triangle by taking VB and BV, AV, VA, and I don't know if you can read this, but this tells me that in position VA there's a 1, in VB there's a 1, and so on. So you have a 0-1 matrix, which we can interpret being over a finite field of characteristic P. So this brings me to the this k-dimensional invertible map refinement over the p-element field. Again, we're giving a graph. We want to produce an equivalence relation on k tuples. And as before, we initially associate all tuples that have the same atomic type. But now during the refinement step, we essentially replace the bijection with an invertible map. So we say that if you consider all indices I and j, we can find an invertible matrix S which witnesses similarity between the extension matrices for all alpha. So in other words, we're saying that if you look at the collection of all these gamma ij matrices over G, the same collection over H, then they're simultaneously similar. So this gives, I mean, so some of the hope we had with this matrix rank game at the beginning was that this would behave nicely as the counting game. And initially we sort of had some idea of, we said like in the bijection game you have bijections, and now you're working over, vector spaces, so what's the corresponding notion, what's the invertible map? But it turned out that didn't really work for the rank game, or seems to be maybe too strong. But so the nice thing is in this setting we actually have this replacement of bijections with invertible maps that gives us a game whose equivalence is decidable in polynomial time, and we have this kind of refinement procedure on graphs. So again, we get an algorithm for testing graph isomorphism, and we can show that for every fixed level k, the k dimension of this algorithm runs in polynomial time, and this is for every prime p. So here's a bit of a mismatch. So the k plus 1 dimension of this algorithm refines the k dimension of this algorithm. And this is essentially because you can think of the way in which you simulate counting is that you need one extra variable to define the diagonal matrix. I mean, clearly one could make the game more complex by allowing counting moves as well. But if your aim is to define to establish non-definability, then this is all you need. And there's a refinement for every, if you increase the value of k, you get a refinement. But we can actually show that for every prime p and every k, we can find a pair of non-isomorphic graphs. They can be distinguished by this third dimension of this algorithm, but not by k dimension of Weishaupt-Lehmann. So that's on the positive side. On the negative side, so the version of the algorithm that I've presented where you have a fixed prime p, that turns out to be a bit of a restriction because we can actually give constructions where if you consider distinct primes p and q, we can actually find for every k a pair of graphs, non-isomorphic. They can be distinguished by the three-dimensional version over g of p, but not by the k-dimensional version over I and q, of I and q. Okay? So that sort of seems to indicate some of the shortcoming of this approach. But I mean, that's partly because of the way in which I define this this algorithm in the game. So just to simplify the notation for this talk, I just looked at sort of matrices that you can define by essentially using two variables. More generally, we allow sort of tuples to index the rows and columns of the matrix. And rather than having a fixed prime, it's more natural to allow a finite set of primes, or allowing the prime to be defined up to polynomial in the size of the graph, let's say. And for those kinds of cases, our proof technique from before doesn't really work. So it's really open whether you can separate this, either whether there are graphs that are not.
Polynomial time when you do these extensions?
Yeah, that's fine. So I mean, either you allow sort of a fixed finite set of primes, or you say I'm going to allow all primes up to some polynomial bound, and with a high rarity, you just exactly, you're blowing up. Okay, so next few minutes I'm going to talk about some open problems. So one of the things we would like to show is to actually.
Are there any kind of examples of graphs that where the WL algorithm fails? No, I mean I'm talking about people who really
Natural problems.
natural graphs, real graphs.
So you mentioned that people actually use this algorithm.
Yes, yeah.
So are there examples where this algorithm failed?
I think it's usually some variant of Weiss Liebman, to be honest. I mean, perimeter, sorry. Yeah. I mean, if you really want to prove, I mean, if you look at, okay, so, I mean, clearly you can find counterexamples for a fixed value, like take k equals 3 or something, you can find some counterexamples. You know, it gets harder and harder as you go. But if you want to prove like counterexamples for all k, then, I mean, the CFI construction is really the only general construction that I know of. And I mean, the problem with graph isomorphism is that it's, you know, again, simple coloring works most of the time. That's why you see a lot of papers claiming graph isomorphism in P, because I have an algorithm and I test it on some graphs and it works. But the hard cases just seem to be really hard to find. So. Okay. So I was going to mention this little problem here. It's kind of interesting. So one idea to get some sort of a feeling for the inherent expressiveness of these rank operators, so not to look at them in the context of fixed points and so on, but just to look at them on sets. So we would like to show that we can actually separate first logic with rank over a prime P versus first logic with rank over a different prime Q over empty signatures. So the crucial ingredient that we seem to need for this is a conjecture that I'm going to state now. So I'll say if you have a formula phi, and I really mean quantify free formula here. So a phi with two variables x and y. We have an integer n and a prime p. I'm going to write this r phi n to denote the rank of the matrix defined by phi over an n element set. So essentially, we have empty signatures, so the only kinds of matrices you have are the ones defined by equality types, if you let this phi be quantify free. And for this kind of setting,
just the diagonal, I'm confused. This is the diagonal matrix. What can you do if you have no vocabulary?
So on
It's only the diagonal matrix.
yes, sorry, this is supposed to be tuples. These should be tuples of, so if you have so if you have
A tuple. So.
x and y should be tuples, arbitrary k tuples. So if you have just two variables, then you have the diagonal, the off diagonal, and so this is one setting. This is another setting, and then you have 0, and then you have 1. So yes, that's pretty simple. So I mean to have tuples there. So this conjecture we have is that, again, these should be tuples. So for every phi, these prime p, we can find polynomials up to the number of elements in the field, such that the rank of phi sort of g of p agrees with the ith polynomial. Sorry, so this value is given by fin for those n that are concurrent to I modulo p. So if this could be proven, then essentially it could be shown by using some quantified elimination and pushing all the nested ranks up to the first level that there would be let's say over g of 3. So let's say you have rank over g of 2. You couldn't say whether the universe has, it's divisible by 3. Let's say. And so we tried to prove this a couple of years ago for using general methods. I mean, clearly, if you have only two variables on each side, there's finitely many quality types, so you can just check it in the computer. But we tried to do using some diagonalization argument, which works for this kind of case, but didn't really seem to lift nicely up to higher tuples. And recently, it's been announced by Daniel Kirsten in Humboldt that he can extend this to essentially 2 by n matrices, but the general case is open. And I mean, as soon as you have the 2 by 2 matrices, the kinds of combinations you have really become non-trivial. So it's really, it's really not obvious how you, like any strategy you have for like, if you have n tuples and n tuples, how you lift it up to n plus 1 tuples, because you have, clearly you have the n by n matrices occurring on the diagonal, but you have also influenced by some of the other matrices. So the rank, it's not clear how it behaves in that sense. Okay, so another problem to actually justify properly or better justify the study of these logics is to give a capturing result on a class of graph. Again, we have the natural here, so on a nice class of graphs, which one where we know that fixed point width counting does not capture p-time. So two of the candidates are graphs of bounded degree, graphs of bounded color class size, and for both of these cases, there's a known graph isomorphism and graph condensation algorithm. So one approach is to try to study these and see whether some of them can be formalized in this logic. And a couple of other questions. So this is an old question. So whether we can, using this logic, express matching in arbitrary graphs. So we know from Albert mentioned on Tuesday that fixed point width counting can do this for bipartite graphs. And this goes back to Moshe's question about these two games. So the question is whether this simultaneous similarity game actually agrees with the natural logic, and also whether it is equivalent to the rank game. And in the next talk, we're going to have more open problems in this field, so feel free to dig in. But yeah, thanks.
Are there any questions for Bjarki?
You mentioned an invertible linear map game.
Mm-hmm.
What didn't work out about trying to use that instance by analogy to the bijection game earlier?
Mm-hmm. Trying to use it to
To characterize equivalence in
right. Yes. So I mean, so that game is in a sense sort of partial. I mean, so if you can give a winning strategy for duplicator, then on a pair of graphs, then you have non-definability in rank logic. So actually, the result that I mentioned about there being where is that? So this result here was actually, so we showed this initially for the matrix rank game essentially, but then observed that the strategy that we gave was one given by a fixed similarity transformation rather than looking at combinations. So the question is, I mean, this is clearly seems to be at least as hard possibly a harder condition than duplicated than in the matrix rank game. But certainly in this case, the strategies become much nicer to easy to describe, because you just have to give one similarity map rather than consider all combinations of these matrices. Does that answer the question or no?
Any other questions?
We mentioned in the middle of the talk that it would be enough to have definability of this simultaneous similarity in rank logic
Yeah. Mm-hmm.
to get the collapse.
Mm-hmm.
So what does it take in the algorithm? What do they use in the algorithm that is not definable? Or
Well, I mean, so what is not definable, or what is not clear whether it's definable.
or what is the algorithm?
Yeah, so the algorithm is to essentially you have to, so you're given these tuples of matrices, and essentially you're looking for how was it again? Yeah, I can't remember exactly. I mean, they're building on a few sort of algebraic algorithms that. What was it, the stabilizer and
moduli.
yeah. So the connection. I mean, so that paper that I referred to is essentially a paper where they're looking at isomorphisms of modules over certain kinds of associative algebras, and that can be reduced to this problem, and they solve this problem for that case. But this builds on some other results. And so I mean, clearly, if one wants to formalize this, then there seem to be like a sequence of algorithms that have to be studied. So
I mean, it's the usual thing. The algorithm is expressed as you take things in order, right?
yeah.
And one has to try and get around that.
Yeah,
So
yeah.
They could express it abstractly without using an order. It's not clear.
So let me suggest another way to extend fixed point logic, which is fix a structure over, let's say, 3 elements, and then have an operator that looks at the formula. The formula defines some relation. Let's say the 3 elements is some summarity, a relation of summarity. So now, whenever you have a formula of that arity, it is true if that structure you define has homomorphism into this fixed 3-element structure, right? We can do it for every, in fact, we can do it for every kind of multi-structure.
Yes, yeah. No, I mean, that's,
This is a way to basically throw in everything we know how to solve from CSP into fixed point
exactly,
logic.
yeah. No, that's, yeah, I mean, that's something we've been looking at.
And then now the syntax is going to be a little different because you have to focus on fixed arity.
Yeah.
It's not exactly what you're doing here,
Yeah.
but it should be a way at least to phrase, because this essentially corresponds to one particular template, the one for the affine case. So should be able to embed this logic, the rank logic, essentially, I think, into
Yes,
that
yeah.
kind of logic.
I mean, right, so I assume you say a fixed arity, so I assume you would have to uniformly look at vectorizations of this or something like
Yeah,
that.
you have to figure out somehow
Right.
to deal with arbitrary arity.
No, yeah, I mean, that's something.
Handle this. I mean, you can think of it instead of homomorphism as a polymorphism. I mean, one has to think
Yeah,
about
yeah.
how to handle general arity.
That's right. I mean, sure. I mean, so we already know from this result showing the, like you say, sort of the non-solvability of linear equations. That there are various other CSPs that are not definable in FPC. So, but I mean, I guess the reason why we started looking at this is just the logic you get is very similar to fixed point counting, and you get a reasonably nice syntax. But obviously, we tried to get an understanding of the limitations of this approach, and then
Exactly. It would be interesting, rather than just defining more expressive logic, to understand why, if at all, this logic can't express. Right? Who knows? Maybe you can do all modes of operations in fixed point with rank.
yeah, it would be
Good, let's do it.
I mean, or it would be interesting to prove you can't.
yes.
Yeah.
But,
So so by defining, by looking at basically and actually defining new proof techniques to actually get counterexamples. In this case, maybe you can get some feeling for why this can or cannot define arbitrary CSPs.
Okay, let's thank our speaker again.